of our paper, but also go into a much deeper analysis where you can use our analysis, but reducing the number of the magnitude range, in computing all the metrics, not regarding the magnitude, but the redshift or the radius, etc. Which I think is really important in this era where we will always have these really complex data sets. Here we can give the community a tool to increase the depth of the analysis, which is limited when you have to write a specific paper. So to conclude these results, I've listed a lot of conclusions here. I will just remind you that this study will help the choice of the algorithm of the Euclid pipeline, which will create the official catalog, so with which all the science will be done. And we've quantified the results on the bias dispersion, on the realistic morphology, etc. Here again, we will have to, or the Euclid consortium will have to do some next steps. So trying to see how the best software performs inside the constraining pipeline of Euclid, and to choose the final software, which will not be my responsibility. So finally, I will talk about one of the projects we've done here again with deep learning to detect and do the segmentation of overlapping or blended galaxies. So a bit of context here again to show you what is blending. So when you observe the sky, you have a 3D volume. So all your galaxies have a certain position in the sky, but they also have a certain depth, certain redshift. But the problem is that when you observe with your telescope, it takes pictures, and pictures are 2D, meaning that all the things that are in the line of sight of your galaxies will be projected into the focal plane, and thus two galaxies that are physically separated will overlap, and we will call this phenomena blending. A good way to identify this kind of galaxies is to look at their segmentation maps. So when you have those two galaxies that are different redshift, you could, if you had them separately, you could create what we call a mask, where which in such an image we put all the pixels that belong to the background to 0, and all the pixels that belong to the galaxy to 1. And the problem, and when you project the two galaxies in the focal plane, you will have this blending. And if you sum the masks, you clearly identify the blending region here. So this is what we will try to reproduce. Blending is very problematic, and more problematic with the new galaxy surveys, because if you look at your focal plane and you have different galaxies that are presented with these shapes, you have a certain detection threshold represented, for example, in green. And what you will observe is everything that is above this threshold. So if you do the segmentation map of those galaxies, what you have is this. With the new large galaxy survey, we are more sensitive than before, so we lower the threshold. And so what you will have is this. And so what you can do is that you detect more galaxies, and the galaxy you observe appear larger, meaning that you increase a lot the probability of having two galaxies that are blended. And this is, of course, problematic for galaxy science, because if you want to quantify and to study the morphology of galaxies, and that instead it's two galaxies that are mixed, it's problematic. But here again, also for cosmology, because here again, we want to measure the shapes of galaxies. And so if they are overlapping, you will introduce a big bias. So because of this problematic, here again, a lot of available software and algorithms, which uses different methods. But we find that they still fail to meet the really precise requirement of Euclid. And in particular, there is an unsatisfying uncertainty prediction and calibration. So in this last chapter, we've tried to overcome those problems with deep learning when we try to predict the segmentation map of blended galaxies from the image. The work is based on the work that was previously done by Bucco et al. And it uses first a UNet. So a UNet is a deep learning algorithm, which is very similar with an autoencoder, where you compress and then decompress the information. But here you just want to keep the information that is necessary to produce the segmentation map. But in addition, what is the difference is that for each decompression step, you take as an input the previous decompression features, but also the corresponding compression information that was made in the same level. And doing that, you will mix all the different scales inside the image, and you will mix those interesting information which produce state-of-the-art segmentation, which are really used in the literature. Problem is that we don't really have a satisfying definition of the uncertainty with this kind of models. So we here again use a work that we adapted from Curl et al., which add a new model that we call here just encoder, which, to be quick, will take the input image and the segmentation to compress the uncertainty inside a distribution. Okay. And then you will concatenate the two models. And what you will have is, for your image, you can pass it through your UNet. It will produce a map here, which is deterministic. But you will also compress the image inside the distribution. And what is good with distribution is that you can sample them as many times, which will give you different samples. And the fact is that you will do a last convolution step where you will mix the deterministic map from the UNet and the uncertainty encoded in the distribution. And what you will have is different predicted segmentation that we can call realization of this image. And what you can start to see here is that when you look at the white part, so a complex blending scene here, you see that there is differences between the realization. And the great thing is that we will be able to use this as a proxy for uncertainty, or a pixel-wise proxy for the uncertainty. So we've tested this model again with simulation, so static profiles that you now know very well. And we've produced the true masks, the segmentation map, by taking all the pixels that are above the Euclid noise limit, meaning that the galaxy is all the pixels above the noise. And so we've trained our algorithm, and the results I will show now were published in a machine learning conference, which we call NeurIPS in 2021. So the results are the following. So here I show two different examples. And in the first column, you have the input image with different galaxies, the ground truth, so the masks that we should recover. And here you have an average, so the mean of all of 64 realizations that we asked our proba unit from this image. And here you have the pixel-wise dispersion between the realization. And what you can see, well, first, we detect all the galaxy, even the very faint here. But what is interesting is that if you look at the dispersion, it is maximum in the borders, the frontier of the galaxy, which means that our model is unsure of where he should stop the galaxy, which makes sense if you think about it, because even physically, it's really hard to say where a galaxy ends. This is the first hint that our model, that our uncertainty, that our dispersion is correlated with the physical uncertainty. The second example I show, this is a more complex scene where you can see here a large galaxy, and you can't see here a very faint galaxy that is blended inside it. So in the ground truth mask, you can see it. Here again, our average prediction is good. We identify the blend region, and in addition, the dispersion is higher on the very complex part of the image. You can also see here a really small galaxies that is cutted at the border of the stem. And here again, our model is able to reconstruct it, to detect it which is also a very interesting feature for galaxy detection. So it's still an ongoing work. What we have quantified about it is the completeness and purity, meaning that we've simulated large field of galaxy and we pass them through our unit, and we look at the completeness and the purity for isolated and blended objects. And you can see that we basically are basically able to detect all isolated galaxies with a very low amount of false positive detection. And for the blended, it's also quite high, knowing that we are simulating and testing up to the Euclid limit. So you can have galaxy, very bright galaxies that are blended with very, very faint galaxies. So to conclude this final chapter, we were able to develop this probabilistic detection and segmentation algorithm with a very good so high completeness and purity, but also a very promising uncertainty calibration without any prior on the galaxy position, which is something that is usually needed for deep learning deblending algorithms. We still have some work to do to quantify the results of this software. So first, to test it against other software to see where we are. Finish the uncertainty calibration, because for now we have just shown that it looked to be correlated and it makes sense, but we need to clarify this thing. And we will try to propose an implementation for Euclid. And the really exciting next step is that we were contacted by the Cosmos Web team to test our algorithm on a real JWST data. So I will now conclude this presentation. So conclude these 3 years of research. So I will take again this pipeline, this Euclid pipeline, to show how I've helped the Euclid consortium. So for the simulation part of Euclid, we've created these complex galaxies with deep learning, and we've started to implement those deep learning algorithms inside the Euclid pipeline to help all the consortium to test every software in more realistic conditions. And I think we've just entered the huge potential of such a model. So for the MER pipeline, so for the MER group to create the catalog production, we've proposed this software of probabilistic segmentation that could, here again, help a lot the production of the catalogs to give a first hint of where the galaxies are and where we have to run deblending algorithms. And we've also created and analyzed this complex morphology challenge to take the decision of the best software to produce the official catalogs. And finally, for the science working groups, we've first used our complex galaxies to give all the people of the legacy science the number they will have to produce their galaxy morphology science, and also forecast the ability of Euclid to recover the morphology parameters that here again are a key to produce galaxy morphology science. So this is for Euclid. Nevertheless, I've tried to work outside of the Euclid pipeline, and more precisely to advertise my work for the astrophysical community with all these meetings and collaborations, trying to show that we can design and democratize the use of deep learning, and more particularly the that deep learning is it's possible to implement deep learning inside such big pipelines. I've also spent a lot of my PhD work to develop these interactive tools that I've just shown you briefly, which I think are really important, both for the reproducibility of the scientific results, but also the exploration to have a much deeper analysis of big and complex data sets. And finally, I've also done scientific outreach to outside of the researchers which I think is not a little thing, which is really important even in those periods where people don't really understand how we do science. I think that giving people the key that people is done with a certain ethic is important, and also give people the want to make great astrophysics. Thank you for your attention. I will now take all your questions, and I leave you with this large field of galaxies that were simulated by our model. Thank you.
Thank you very much, Hubert. Thanks a lot for this very nice presentation of your work. So we are going to start the session of questions. And just to explain to the audience and also to the member of the committee, so we'll start the questions by the specialists. So we will start, in fact, by the referees, the two referees. And then we will go on with the examinateurs, sorry for the French way of pronouncing it, and then finish with the supervisors. And I suggest that we finish with the local supervisor to allow for, let's say, for politeness, having the first go to our guests. So for those of you who are members of the committee and not used to the way it goes, there are no, formally, there are no limits to the number of questions that you can ask to Hubert. So you can be not shy if you wish so, but just bear in mind that we're several people around, and that if we don't want Hubert to collapse eventually, we have to be a little bit, let's say, reasonable. So this being said, I suggest that we start with the questions from the first referee, Laurence Levasseur from University of Montreal remotely.
All right, so I'm going to be the one starting with my questions. Nice. Okay, so maybe I'm going to start by what you talked about at the very end, because I am particularly interested in doing difficult inference problems. And so your discussion about finding uncertainties with deep learning methods is of great interest to me. And sorry, before I start with my questions, thank you very much for your presentation. It was very nice. I really enjoyed it, and you did a great job, and I think you did fantastic work for your PhD. It was like, I really enjoyed reading your thesis. It was a really great thesis to read. So I just wanted to say that first. But yeah, so about the uncertainty part. So first of all, I would like to hear you a little bit more in details about how you're planning on quantifying how good the uncertainties you are getting, like how well calibrated they are, to be a bit more quantitative, like if you have some ideas about the kinds of things you can be doing to quantify that. And then I would like you also to tell me if you have any plans or if you have any ideas about how you would look at the epistemic uncertainties of your model. Because, like, for example, the way I see it now, if like your two latent spaces between your like I forgot how you call it in your thesis, but your prior network and your posterior network is a little bit different, and it will always be different because your training is never perfect, then that's going to introduce some sorts of error. And so, like, I was wondering if you had any idea on specifically how you would go and quantify that.
Yes. Okay. So for your first question, we have ideas to test and to calibrate this uncertainty. So when you take the mean of your realizations, so your background probability will not be just 0. It will be a probability between 0 and 1, and the same with isolated pixels that will be between 1 and 2, and etc. And what we've started to do is you can then say, okay, my galaxy is blended if there is a pixel inside my galaxy which is between 1 and 2, meaning that at least one realization contained a blended pixel. And what you can do is that you can move the threshold, meaning that, okay, you consider that your galaxy is indeed blended if there is 20% of your realization that shows a blend region. And you can look at your ROC curve, so your true positive rate and your false negative rate. And it will move inside this ROC curve depending on your threshold. And here you can look if your coverage probability is well calibrated by calibrating this threshold, which is a first way, yes, to do the calibration. For the second question, so yeah, I think for now we more look at the aleatoric uncertainty, not the epistemic one. I'm not sure if we stick with this kind of algorithm, we can really probe the epistemic model, because it's not at all a Bayesian network. We could try to do MC dropout, for example, to see how our uncertainty change with MC dropout. Not sure that this is still satisfying to find the epistemic probability. So yeah, I'm not sure with this kind of model we can directly probe the epistemic probability, which is a problem. I agree.
So would you have any ideas of what would be a good path forward to like sort of have more statistical confidence that when you're saying an uncertainty is like this much, this is 1 sigma uncertainty, then this is actually, you actually really mean 1 sigma, taking all the uncertainty of your model into account?
Well, I mean, if we show that our coverage probability are met with a certain threshold, we could say that it englobes both the epistemic and the aleatoric part of the model. To distinguish between the two, I don't think so, and I have no clear idea on how to do this. Nevertheless, in this kind of detection segmentation, I'm not sure we really need to separate the two. If we show that our uncertainty is calibrated, to know exactly how we perform the task is not the primary problem. It is, of course, but this is a kind of problem where deep learning can be used not like that, but yeah, I think you get my point.
All right, thank you so much. All right, so I'm gonna try to not ask, I have a lot of questions. So I'm gonna try to keep it short so that other people can also get a chance to ask questions. Okay, so I have a question about the other part of your presentation when you talked about the challenge, the analysis of the results, when you showed the dispersion that was the error, like the trumpet plot that was very different between the sort of parametric simulations versus the more realistic simulations that were taken from your deep learning simulations. So yes, this slide exactly. So like obviously you have much larger error in your when you have realistic simulations. That's to be expected. But I was wondering if you had given some thought or made some analysis for what does that mean in terms of biases that you would get in the inferred signs that you would want to extract from those parameters, more like quantitatively. Have you thought about what specifically, what kind of impact that would have? Where would that error need to be for you to have no bias? And for example, like obviously for recleansing sciences, this is presumably where this is going to have the largest impact. But if you have, like if the error that you introduce is kind of uniform and unbiased, are you really going to bias the results that much? So I would like to hear your thoughts about this.
Okay. Well, I haven't, to be clear, I haven't quantified how this uncertainty will be propagated through the pipeline. Nevertheless, I think that, for example, for the axis ratio, it's clear that it will impact your weak lensing measurements. If you're biased in your ellipticity, you will be biased in your weak lensing measurements. The direct relation between the two, I can't say like that. But yeah, I know that, for example, for blending, they directly show how the blending in LSST will impact the weak-lessing measurements. So it's, yeah, I know that there is some ways to propagate the uncertainty through all the pipeline. We haven't done that here. But if I can add a thought about that, is that on a realistic condition, it's even difficult to define what is the true ellipticity of, I don't know, a spiral galaxy or irregular galaxy, which means that we have a higher error, but on what? On a ground truth that we don't really know, that we don't even know. So I think this is really difficult to propagate the error, because we are always thinking of galaxies as static parameters where you know the ellipticity, but do we?
Yeah, exactly. That's a very good point that you're mentioning. So just a little bit more on this. So do you have some understanding of where is it that the algorithms that you tested or that submitted answers to the challenge, like where is the main source of error coming from specifically for those algorithms? Do you have some understanding of what is it that is missing? Like, is there something that you could be done very quickly to in terms of like increasing the complexity of the parameterization? Yeah, do you have some intuition about what's missing basically in those algorithms?
Yeah, so yes, there is the solution of increasing the number of static profiles that you fit to your galaxy. I know that for local universe galaxies, which are very complex, they try to fit not just a bulge and a disk, but much more parameters. I'm really not an expert about that, but when we look in our analysis of double Cerseic galaxies, we already show that the bulge is basically very hard to predict. So I'm not sure that adding more parameters, theoretically, it's nice because you gain freedom in the way you model your galaxy. But if the software can't really do it precisely, I'm not sure the solution is here. So the other part will be to make the algorithm better at that task. But yeah, I'm not an expert on that. I know that there is a new algorithm in the market using deep learnings and VAEs for specific tasks. Was a shame that they didn't participate in the challenge, but I think they are really promising. And in addition, they have a really good coverage probability. So I haven't the name here, but I can show you that, and maybe it's one step further. For example, with deep legato, we show that the results on the faint end is really good. I guess there is a way to make the algorithm better, but
do you know why Deep Legato didn't submit an answer for the more realistic galaxies? Is it because their algorithm was not working at all, or is it?
We don't exactly know. We know that the people that were working on it was a bit outside of the research when we finalized the challenge. So could be just a human power problem. But it's a shame because we, as you know, it's great to look at transfer knowledge. Yes. Yeah, we were not able.
All right, thanks. All right, so I have another question about like maybe the first part of your thesis about your generator, your generator, your flow VAE. So I was wondering if you could comment on how like the distribution of training set that you have could bias the accuracy of the distribution of the galaxies that you're reconstructing through your method. Like, for example, because you're conditioning on like a certain number of parameters, but presumably if you're in your training set, you have very few realization, those parameters are going to occupy like a really small region in the probability region in your latent space. So when you sample, you could be sampling with very different distribution from the variables you're not conditioning on. And so I was wondering if you had some thought about this and what you could think could be a fix to ensure that you get a good distribution of galaxies that's really representative of the galaxies we have in the universe, besides maybe just conditioning on everything.
Yeah. Well, I would start by saying that the problem is even more problematic, knowing that the low end, the high magnitude ends are the galaxies that are the harder to simulate, and this is the one that we have the less in our data set. But saying that, what we are trying now is to, so we've shown in our second analysis on the morphology capacities that, for example, Euclid will not be able to detect any complex structures with magnitude over 22. So what we could do is to train our network on a reduced data set, meaning that we don't need to simulate blobby galaxies that will not be resolved as the structures galaxies. So this could be a first way to see what is the change on the two algorithms. Not be a solution, but it could be a first test. One thing, I don't know if it answers the question, but what is usually problematic with variational autoencoders is that you force the regularization, and so you force everything to be close, and it's sometimes and often decrease the complexity of the simulation you can do, because you force everything to be smooth. With this kind of flow VAE, because you will not be sampling from a normal Gaussian, because you have your flows that will produce different realization, you can relax the constraint on the KL, on the beta of the beta KL, which I think we didn't explore that, but I think we could do this. So for now, we've trained our flow VAE a bit like if it was just a VAE. I think we could relax the constraints, and maybe we'll gain here again the production of complex galaxy, even if we had a few number in our training set. Yeah.
So in practice, how do you do that? Do you relax it progressively? Like you start with like a large beta, and then you train your flow, and then once the flow is trained, you retrain your VAE with a different value of beta until your beta goes to 0. Is that what you have in mind?
No. What I would do, so for now, what we do is we start with so the VAE and the flow are trained completely separately. We first train,
yeah, exactly.
And how do we train the flow? With increasing beta. So we start with no constraint on the latent space to ensure that we are able to learn complex morphologies. And then we increase the beta such that the latent space is more regularized. What we could do is just simply increase the beta less to stop.
So the latent space of what? Of the VAE or?
Of the VAE. And then
I misunderstood what you did. Wait. So you train the flow first or the VAE first? Because they're trained separately, right? I thought you trained the VAE first.
Yeah, I trained the VAE first with the beta that tells you the importance of the reconstruction term and the importance of the term. And the way we train this is by increasing the beta through the training.
Yeah, which is typically how you do it.
Yeah. At a quite high value of beta, meaning that we really force the VAE to be regular, which in practice we are not forced to do it, because then the flow could learn a more irregular latent space. So by limiting this value of beta when we train the VAE, we could the flow doesn't care about the regularity of the VAE. So I guess we will be able to produce more galaxy and more complex galaxies. Yeah. I don't know. Maybe
I guess I have another. Thanks. That was super insightful. I have another kind of maybe more basic question. How do you quantify how different the distribution of the galaxies you produce is from the distribution of your training set?
Yeah, this is a big point. So the only test we can really, well, we did, maybe we have others to do, but first to see if a galaxy is indeed realistic is very complex, because you know that the matrix of the reality of a galaxy is complex. So what we've done is a visual test, and we're based on in François' work. He also looked at the CAS parameters to see if globally all the galaxies that were simulated, when you fit the CAS parameters, it retrieves the good distribution. Meaning that in terms of CAS parameters, our galaxies are overall realistic.
Mm-hmm.
So we've not redo the test with that, but we've used the same flow VAE. So yeah, and then with the test we've done is more on the flows, on the conditioning. But here again, as I said, it's quite problematic because the only way to find if your flow is well conditioned is to use fitting algorithms, which are tested on SEARCH-6 profile. And so we show that we have more bias, and it's what is shown also in the morphology challenge. We have more bias and more dispersion in the realistic morphology. But is it a problem of the software algorithms that can't fit it, or is it the problem of the conditioning of the flow? The aspects are completely mixed. It's really hard to distinguish between the two. So yeah.
All right, thanks. All right, I think I've been asking questions for almost. Okay, so maybe I'll ask one very general physics question because you had such a nice introduction in your thesis, and so I'm just going to ask you one. Just one physics question. Okay, so when you talked about, so it was about the part where you talked about what was it, the Einstein's equations, and you were deriving the FRW metric. So you use the FRW metric to find Einstein's equations, and then you were using the continuity equation to get an expression for H, I think. And so you said that, basically all the Einstein's equation, you get two equations, and then you have the continuity equation. You can basically combine the two to get an expression for the pressure or the density in terms of A. I think that's, so did you know what I'm talking about?
Yes.
Okay, so you said that in order to do that, you need to combine the two Einstein's equations, which is kind of like redundant. And then you need to use the conservation of energy. Okay.
Yes.
But so my question is, so in physics, you probably learned that conservation of energy happens when you have translation symmetry, right?
Yes.
But in the universe, the geometry of the universe is constantly changing in an FRW universe. And so why would you expect to have conservation of energy then?
Great question. So there is also a problem, right, that the universe is a small open system, that you don't really have this closed system, or you can say that you have the conservation of energy. So I won't be able to say like that why. And combine was not the good term. I know I used.
Yeah. Yes.
It's all these equation, use them as first steps to derive the other equations. But yeah, no, I'm afraid I won't be able to answer this question.
It's food for thought. But yeah, so you should think about it. It's interesting. because yeah, exactly. So there's no reason for energy to be conserved in the universe if you think about it like the way I explained it, which is a fun thing to think about. But so if you want me to give you some clue, see, the answer is that you can sort of write the equivalent of energy sort of goes into the geometry. And so if you go back to the same, if you go backward in time, you recover, the energy doesn't, if the universe was sort of reversing its expansion, you would go back to the same amount of energy. Okay. If that makes sense. But it's something interesting to think about. All right, so I'm going to leave it here.
The time translation, if you break the symmetry, you break the. You don't want to do that.
So thank you very much for your questions and for giving us some material to think of. I'm sure that in the audience, other people will think of your question. And we will turn maybe to the second referee, who is Stéphane Arnoux from CNRS in Marseille.
So thank you. That was a great talk. So I really enjoyed this. It was very nice introductions, both on the deep learning, which I'm not an expert, and also on the galaxy evolution part. So we go through the different. Right. I will go through the 3 chapters just and a few questions. When you use the candles for the training of the real galaxies for the chapter 3, and you simulated real galaxies, so you use the candle sample,
the cosmos,
cosmos sample, and the parameters that you use are just magnitudes, CR6, ellipticity.
Yes.
You never include the redshift.
No.
In this one. So since there is, you are fixed in the passband, which is I band or one of the passband in candles or cosmos sample.
Yeah.
You have the kind of morphological corrections
that
enter in act, and this information is kind of lost then in your set of parameters. So, so my question is, when you go move at high redshift, you know that this correction, morphological correction, will induce more clumpy galaxies in UVs that will go in your optical.
Yeah.
So so then, will this impact the way you characterize at the end the structure on your galaxies, the fraction of galaxies that have structure? Because indeed it is not that obvious that you can recover this correction.
Yes.
That was neglected at the beginning.
Yeah.
So any thoughts how to handle this aspect, and is it really a matter, and how can you handle it?
Yeah, I think it's one of the possible limitations of our study. What we have is that we also condition on the magnitude, and there is a correlation between magnitude and redshift. Like higher redshift galaxies has a lower observed magnitude. So it's on the observed magnitude, which means that if we ask, so all the galaxies we've shown, it was looking at the magnitude. So we only looked at galaxies that have we asked the flow to produce galaxy with a magnitude, I don't know, below 22. And those galaxies will have a redshift, which is correlated to this magnitude. If we ask for a magnitude of 22, it will not be a galaxy at redshift 2. So this mitigates a bit the problem, but not totally. And one easy way to do that will be to condition the flow with the redshift 2.
But you haven't tried it?
We didn't.
Yeah, I don't. Okay.
So, yeah.
And also,
and we would need the redshift measurements on Cosmos.
You use it so at some point, so
you
have it.
Yeah.
So but I think it can just with respect to the fraction of structures that you can detect, because you have a nice way to characterize the number of structures that you can detect, which is nice. But maybe the point that in the cast distribution you tested, or in the previous papers they tested, that seems to reproduce correctly the distribution.
Yes.
Even if you look at the paper. So this is maybe the way to say that is not as drastic impact.
Yes. Yeah, but the problem is that maybe when we ask for a galaxy at magnitude 22, it will, right. Probably
still,
can be.
You can still get those type of objects. One more question here. It's about one figure that you haven't shown here. I was a bit worried about this bias. It seems that with the flow VAE, the recovery of the axis ratio was not that great. So do you have a kind of a bias of the axis ratio in figure 313?
Well,
so you haven't shown it, but is it really a matter of concern, this bias? Because it's exactly one of the parameters that may be important for Euclid. And so do you have any interpretation of this? Is it due to the techniques, or maybe some lack of training for this type of axis ratio. Do you have any clue about what could be the origin of this effect?
So as I said, the two things can be that the flow is not well trained, so it doesn't produce the good ellipticity. But it can also be that the software doesn't recover the good ellipticity. And the two, you can't easily distinguish between the two effects. And if I remember the figure, we have shown that this bias is even higher in the low magnitude, I think, so the bright objects. And here again, the two effects that this is a problem of the flow or this is a problem of the softwares is correlated, because it can be that our flow is well trained, is worse trained on bright object because we have less in our training set. But it can also be that bright objects are more complex because and so the fitting is harder, because what is the ellipticity of a complex galaxy? So here again, it's hard to say if it's a problem of the fitting software of the generating software.
So it can be a problem of the prior distribution.
Could be.
You tend to not populate well with the flows,
so this
the tail.
Not really, because we've looked at overall so if you don't take galaxy by galaxy, we show that the distribution is the top and the left panel.
Yeah.
You show that basically we recover the entire distribution. It doesn't tell you that this galaxy is well trained, but the VAE, not looking at the flow, the VAE is able to reproduce all the ellipticities. But maybe the flow is not perfectly trained.
One general question about this deep learning approach. So in both of your cases, you have a combined loss. So you combine the KL, and you have a beta term for the KL divergence plus MSE. And so the way you want to combine these two loss to optimize your problem is not obvious at all.
No.
And how can you tune this extraction of meta parameter, or I don't know, hyperparameter that you use in this? Do you have any idea of how you can optimize the tuning of those parameters?
So one way is to, and for example, I use TensorBoard to see the training. And one thing you can do is to look at the images during the training. And for example, when so if you remember, we increase the beta, for example, during time, and you can see if during the training, if indeed the galaxies are more complex and then become a bit less complex because you're increasing the beta, etc. And so you can find a balance looking directly at the images. The other possibility, I don't know, if at the end you show that you are like a bit of a mode collapse, and you see that you only produce around the galaxy, could mean that your beta is too high, and then you should decrease it. But it's a posteriori. A priori, it's difficult. You as I said, the fact that you increase beta, that you decrease the learning rate, things like that are common good practice in deep learning. But then when you have the hand on the thing, you usually have to tweak the hyperparameters. I mean, there are no great perfect rule.
Yeah, this is
and looking at the losses.
For this beta, I see, but for the other one with where you combine the three
weights,
where you mentioned that you can at the end you prefer to use loss which is weighted according to the importance of the different classes that you are looking at, rather than doing that data augmentation for the class with an unbalanced or underrepresented class.
Yes.
You don't choose to go through data augmentation. So is there a balance between the weighting the loss in one specific way or doing some data augmentation?
Yeah, here again, you can do it a posteriori, trying different things and see the results, as we discussed when we show that weighting the losses, you converge faster, but not better. So maybe we should try the other way. As I said, I'm always concerned when you do too much data augmentation, because it means that your algorithm, I mean, you bias your training sets, which is, I think, not a good practice, because it means that you learn a universe that is not the one. But then if you do transfer learning and things like that, it means that you could do it. But yeah, maybe it's just a personal preference.
When you weight your bias as well, no? You give more importance to this. It's another way to.
I'm not sure it's exactly the same problem.
It doesn't seem to be the.
No. No, yeah.
But yeah, that's something which is not.
You say to your network this error is more important, but you don't show it more. You don't show more examples of this kind. I think there's a difference. But this is interesting.
Yeah, and so to come back on the unit, so the second software, so I had some problem to understand exactly the architecture.
Yeah.
And so my point is for the lowest part, so just the unit.
Okay.
Why can't you get a kind of probability directly with the bottom part, directly with the unit, without using anything on the top? So because basically you can have you do your training with the good truth and with the ground truth, and so you can end up already just with the unit, with the probability.
You could, but I won't trust it, because we know in the literature that usually this uncertainty is not at all correlated with your nor epistemic nor aleatoric uncertainty. So but we could try, but we didn't.
You didn't compare with what you get with the person. And then, but so the nice thing with the unit, you can really train the different component background, and blended galaxy with the right fraction, because you give real images, large images, so you have all the fraction, the right balance of the different class that you are looking at.
Yes.
But then for the upper part, since the probability that you want to extract is really to focus on the blended galaxy, which are extremely underrepresented in your sample, could you train the upper part independently of the bottom part in some way, and just or do a pre-training of the bottom part and then make another training with maybe not data augmentation, I don't know how I should say, but with more galaxy with blended, with blending effects, so that you properly, you may have a better way to define the probability for those subjects, which are the ones that you are interested in most at the end.
It's a great point. I know what you mean. I haven't really thought about it. It's a great point. That's the dispersion could be broader just because he's not used to see this kind of objects.
Exactly. You just haven't seen those so often, because basically you have 90% of background pixel and maybe more.
Yes. So here maybe adding more
realization of
blended. In fact, I've tried it. So to first train on only blended objects, and then pursuing the training with a real world training set. I haven't quantified the results, but it's definitely something to check, to see. I think it's also the point of Laurence, that this could be just an epistemic uncertainty, because just your model is not familiar with this kind of image, which is not aleatory. Could be a way. If you see that your uncertainty decrease when you train it with more of these objectives, it means that it was just an epidemic problem.
Okay, thank you. On the last chapter, how deep legato was trained? He used a part of the sample that you provide, or he was trained on something completely different?
So the paper, on the official paper, it was trained on, I don't know really, but for this morphology challenge, yeah, he used the same kind of simulation, which is
okay.
could be problematic. In this, but we stated it in the same way that the other algorithm adapted their priors with the knowledge of the training set, which is and even it's not cheated because we didn't.
Sorry.
Yeah.
The chairperson should not speak.
But yeah, sorry, I need to answer the question. So you can see here that there is here on the purple plot, you see that there is a discontinuity here.
Yeah, between the two modes of
and this is because deep legato is trained as two different set of weights. So there's two deep legatos, one which is trained on faint objects and one which is trained on bright object. So, but yeah, it was trained up to the magnitude limit 25.3.
The results are really impressive at low signal to noise. It's really quite remarkable.
In the outlier fraction and in the bias.
One interesting point is that you had about Sextractor plus. So Sex.
Don't correct the referee. Do not correct the referee.
And so you might, he's the only one with doing fitting that is able to get relatively high accuracy at low signal to noise. And so you mentioned that it could be related to some prior in bulge to total or bulge to disk prior at center, or at least to start with.
Yes.
And so did you try to check this if this is really true? This because you can plot those results as a function of bulge to disk or bulge to total and see if there is a trend to have a bias which is above or below zero, and zero when it's close to the initial guess. So did you try just to see that if there is really a bias and this bias should go in one direction and the other?
No,
on both sides of the prior
but
initial guess.
And we can do it easily with my web
with your tool,
platform.
exactly. That's a nice way to use your tool. Check that.
But yes, it could be a way to.
I think it's at least it can validate or not with idea that the bias.
Yeah, the idea is like if they always, it's like the non-positive that we've discussed. If your prior is 0.1 and all 90% of your data set is 0.1, you can just predict 0.1 and you will be right 90% of the time.
Exactly. And finally, in those tests, because they are really important, all these tests for Euclid, and so to loop on the blending sources that you discussed before in the other chapter. So, did you look at the impact on the axis ratio for blended sources with different level of blendiness to see how it impacts on morphological measurement? Because you mentioned it since the beginning of the first pages of the thesis. You end up with these results here, and I think you can explore directly on the blended regions what is the impact on the axis ratio and how strong it can be for the weak lensing measurement. So it's kind of a loop of.
We didn't, but I agree.
So that's that will be interesting to have this type of.
The thing is that as we showed in the forecast of blending for the wide survey, it has not such a big impact. So we didn't try to by saying that it's a 3% or 5% of the
galaxy
galaxies.
will be done with white survey, essentially. So in the introduction, just so you mentioned that we are in the accuracy cosmology, and so we need to control the systematic.
Yes,
and this is true. But don't you think that the machine learning can introduce its own systematic in the game, and then
Sure.
bias a bit also the result in his own way.
Yeah. So it's one of the tools. We can hope that it's better in certain precise cases, but it's not perfect, and that's why we really try to tackle the uncertainty prediction thing, because we are going to be biased, or we will have a dispersion. But first thing, if you are able to quantify and to calibrate it, it's a first good thing. Which for, I don't know, I mean, we've looked at even in the blending algorithm, it's often the case, even classical algorithms, the uncertainty is not perfect. So I don't say deep learning is perfect. It's one of the tools we can investigate.
And to push in the perspective of all this work,
Yes.
with deep learning,
Yes.
so there is the CAS parameters that are frequently used and so on. Frequently used to go beyond what you can do with CR6 index and
Yes.
parametric approach. Did you think about? Did you start thinking about what you could do with machine learning to develop a new CAS approach or new parameter space with deep learning that could drastically help the classification of morphology beyond the CAS parameter?
I think the good, great thing about deep learning, and especially unsupervised deep learning, is that you can learn a new classification with that, which is not limited by the fact that you need to put things in boxes, as we do during all the theses, saying that, okay, this is this electricity, this may, but even with CAS parameters. Here, when you project, I don't know, in a SOM or in a t-SNE or thing like that, so in a latent space, and there's works was done. If you can then do like k-means to cluster the subject, you can see that things cluster without any, we didn't force to say, okay, this is because this is the asymmetry, this is concentration, and you didn't put anything. It's just that in the image, there is something that correlates the subject. And it can give the new hint of classification. Yeah, new classification, even if it's not mathematical, but just the deep learning. If the deep learning classify those together, it means obviously that there is something in the image. Maybe it's not interesting, but there is something in the image that classifies those galaxies together.
You should not help him as well to not go in the wrong, to use wrong parameters to do the clusters.
Yeah.
So is there a way to mix and balance unsupervised and or semi-supervised approach to do this type of?
Yes. So with self-supervised, where you force the network to learn only the physical things, so you don't precise which physical things, but you remove the one that you don't want. So you do data augmentation, where you take your image, and for example, you say, I don't want my model to learn the orientation of the galaxy. So you take your same galaxy and you turn it. Then you change the PSF because you don't want to be dependent to the PSF. You do all the augmentation that you want to remove from your classification, and you make your network learn that all those galaxies that are the same but seen differently need to fall in the same place. And then you put all your galaxy, and you find now a classification that is not dependent on the instrumental effects, for example, which is exactly what you do.
Well, just
You should have not said yes.
well, and you talk about the SFR mass relation.
Yes.
At the beginning.
Yeah.
And you see how important is the classification by morphological type, because ellipticals are the ones that are quenched, and the star forming are. But even inside the star forming, I think using the morphology is also important, because the SFR mass relation, the stellar mass includes the bulge. So I don't know if you have seen, but there are papers that claim that when you remove the bulge, so you just do the measurement of the disk, the star formation efficiency is constant. It doesn't change with the mass of the disk. So there is a kind of a bias when you put the mass with the bulge. you bias your measurement and you
Consider
expect the star formation efficiency to be lower on high mass and higher on low mass. But if you really make a careful job, so the morphology is really crucial in this type of thing. Do you see any other application that you could do in this type of vein by using morphology to just start to improve our knowledge about the star formation activities in galaxies? That could be of major interest, like clumps, measurements of clumps and high redshift galaxies to understand the.
Yeah, if you're able to classify all those objects together, then you can investigate the different groups together and look at all the different parameters and see if there is a, I don't know, like a new correlation. I don't know, like the different planes that you have in galaxy science. Maybe there is some that correlates. So we know that there is this relation between the velocity, dispersion, and early or late type. Maybe there is more when you look at more specific class. So maybe, yeah.
All the fundamental planes
all the
relations
fundamental
can
planes.
be redesigned in
Yes.
some different way to illustrate this. So
There's a lot of things to do.
Yeah,
Yeah.
sorry.
Thank you.
Thank you.
Thank you very much, Stéphane, for this thorough discussion. So we will move now to the examinator of the PhD thesis, and we will start here with Elena Dominguez Sanchez. Please go ahead.
So first of all, I want to congratulate Hubert for this extraordinary PhD work. It is an impressive amount of work which has been carried out in 3 years, working with very scientifically important aspects and state-of-the-art techniques and data. And this work is very nicely summarized in the PhD. It's very easy to read. It has a flow. It's very pedagogical. So I want to congratulate you for that. And also very important, it puts in context why your PhD is important and why you have done all this, and it will be relevant for future works. So because you've done such a great work, I'm going to start with a tough question. And since Euclid is still in land, it won't be launched for a few years. If you could improve something from Euclid for your data science, for example, the connection between morphology and star formation history, what aspect would you change?
In Euclid.
In Euclid.
So yeah, and with real data, like what should we?
Exactly, the capacities, maybe spatial resolution, wavelength coverage, larger field.
Yeah, well, larger deep fields, if you want to do galaxy morphology.
Larger deep fields.
Yes, because deep fields are for now, compared to the wide field, really small. I guess adding bands, I think filters is always a good thing. Spatial resolution, of course, but I mean, you always want better. Choose one. I think that, yeah, I think the resolution is okay, and so maybe just bigger deep fields.
Okay. So I'm going to move now to chapter 3 with your variational autoencoder.
Yes.
If I understood correctly, you generate the bolts and the disk components separately.
Yes.
And then you merge them together.
Yes.
Is there a reason why you did that?
Yes. So we've developed mainly this algorithm to work on the Euclid pipeline, and the Euclid pipeline produces bulge disk decompositions. So for example, the catalog, you don't have the size of the galaxy. You have the size of the bulge and you have the size of the disk. So this is the first limitation, because if we wanted to simulate just one galaxy, one profile, we should work on how to transform the double Sersic catalog on one single Sersic, which is doable. And indeed, for the morphology challenge, we've done that. So for the morphology challenge, we used a single Sersic description of galaxies, which is indeed the natural behavior of the FVA, because the VAE was trained on real galaxies, and the flow was trained on the description of the single CERSIC profile. So the best answer, which is constraining and not a bad thing, we could have exploited the VAE, but it was to work on the Euclid pipeline, because we wanted to show that our model was usable in the Euclid pipeline, and to do so, we had to compare exactly with what is done in SIM, and what is done in SIM is double CERSIC galaxies.
And then when you compare, so the loss function of your reconstructed images and the Cosmos images is with the combination of the bulge and the disk, or the two components separately?
The two components separately.
Okay.
And then we just said that the bulge is a specific type of galaxy, which is a bulgy galaxy, which is a limitation, I agree.
And could you have trained your the two components, mix them together, and then compute the loss on the two component galaxies? Because Cosmos galaxies are complex systems that
Yes.
may have these two components.
We could have what we didn't, and I think the morphology challenge gave us reason. We had a good way to do that. Is that so there is a catalog of describing the Cosmos galaxy with two components, but can we really trust it? I'm not sure.
Well, I think it has biases, as it has as you have biases when you describe the galaxy with one component. So again, you have to find a trade-off.
But I mean, when you look at the bulge disk decomposition of the morphology challenge, you see that the parameters of the bulges are very biased and dispersed. So using that as a ground truth, I mean, both approaches have problems.
Mm-hmm.
The best way for me is just to simulate single CERSIC. And because it was learned on complex morphology, it will produce complex morphology, but they will be described, they will be conditioned with only a single.
And following towards that direction, when you fit your complex galaxies with CERSIC simulations, and we see that the errors are larger, and we all agree that this is because galaxies are more complex, but it could also be that the fact that this ground truth becomes distorted. Did you do the test with the two components for these galaxies?
So two components, realistic morphologies.
Yeah, to do a two component CERSIC fit to the complex simulations.
That's a good point. So we didn't analyze that. I think Galapagos 2 have this because the basic, the default mode of Galapagos is to do both single and double together. Yeah, it's a great point to look if the double fitting is maybe better because the morphology is complex.
Thank you. I was really surprised, and I thought it was a very clever idea to use the second derivative to detect the structure, as you state in section 3.4. Is it a new approach? Does it come from any publication, or was it your own idea?
It was my own idea. Yeah, so I was looking how can I easily separate the two things, and taking the advantage that my simulation are noiseless without a very low amount of noise. And so I tried different things, and I've looked at this kind of and I tried to see what is really the difference in the profiles. And I say, okay, maybe there is this double thing, and I worked a bit on that, and I see that it was indeed separating, not perfectly, of course, but it was another way to distinguish instead of the cast parameter, which would have been harder to compute.
I think it's a very clever approach, and I think it will be worth exploring further and compare it maybe with the residuals of a CERSIC fit. You also say in the PhD that when a CERSIC fit has residuals, it's because you cannot describe the galaxy with a very simple parametric fit.
Yeah.
Okay, so chapter 5 is also very impressive. The amount of work you have been able to extract and try to gain insights on that. I think the interactive tool was the only way to be able to summarize all that information. So I was very surprised when, after all that work, you use the same outlier fraction for all the parameters to be 0.5.
Yeah.
Could you comment on that?
It was for simplicity, because the analysis was already quite complex, and thus to find the good outlier fraction for every parameter. I mean, yeah, at the end, there is no good answer. So you can try to tweak it to have your own definition, which will never be perfect. So in our case, we decided to put it at 0.5 for everything. It's what's not random. So we tried a lot of others definition, like to try like the 3 or 4 times the medium dispersion of all codes, doing that by bin of magnitude, etc. We found that there wasn't changing much at the cost of a twice longer paper, which is already too long. And you know,
I would have changed that at least for the Cersei index, because 0.5 it's a very small error for.
Yeah, but it's a log
for
10.
the large Cersei index.
But
So
it's a log of the, so it's the error on the log of the
error on the log. Yeah, that makes more sense. Okay, so I'm gonna end up with a very general question. What was the most challenging part of your PhD, or the part that you feel more proud about?
The thing I'm most proud of, I think, is the interactive tool, because I think, well, it's fun, but I think it's something that more people should do, because it's a shame when you spend so many times to analyze a data set to just choose the 5 best plots, put them in a paper, analyze them, and it's over. I think it's a powerful approach. So I was happy with the results and all the possibility it can make. And the most challenging is also, I think, the morpho challenge, the analysis.
Also a little bit boring, you know.
Yeah, challenging, I would say.
Thanks a lot, Hubert.
Thank you.
Thank you very much, Elena. So we'll turn to Brant Robertson from UC Santa Cruz, remotely.
Good afternoon or good morning for me. There have already been a lot of really excellent questions, so I'll try to limit my scope here. One question I had was about the information content in the images produced by your VAE. You know, in looking at the examples that you provided, of course, you know, you're trying to simulate galaxies on the pixel scale and with the resolution and sensitivity of Euclid. But the individual information content of those specific objects seems perhaps somewhat limited. And I was wondering if you've looked at how well the VAE model works for galaxies that have more pixels, meaning more information content, extended objects that are better resolved because they're closer by. How does the model perform by some metric for galaxies that have more information content in them than what you've shown here?
Yeah, that's a good question. So we first answer is we did not. But the problem is, and I would be very happy to discuss that, is what metric would you use to define what complexity? I guess there is, because you can identify how complex an image is, but complexity doesn't mean realistic. And so even if you show that your images are complex, this is the first good thing, but if maybe they are too complex because the galaxy is not that complex. So it's the first step, but yeah, I know I don't know exactly like that an information metric that you could use, but I guess there is.
Yeah, so that brings me to another question. Some of this was already raised by Stefan, but you know, when it comes to evaluating what is realistic, you know, really that's a way of us summarizing the information content of an image in a way that to us seems realistic. And in many generative models, when people are trying to produce you know, images of people, for instance, there's a perceptive loss that people add that tries to influence the outcome of the generative model to look realistic to human eyes. When it comes to galaxies, of course, we have some sense of what we think looks real, but quantifying that can be a challenge. You know, I was thinking that there might be statistical ways of doing that. And I was wondering if you'd looked at, say, wavelet decompositions or other decompositions where statistically you're quantifying the frequency of features, either in wavelets in terms of their size or other decompositions that have you know, some quantification of the information content in terms of different modes that appear in the objects.
Yeah, could be a good way. I mean, there is a CAS and the other non-parametric metrics, but yeah, wavelets could be a good thing. I've also just thought about we can also use some, for example, generative some adversarial networks to compare between real galaxies and our galaxies. Problem is that we need to find pairs that are similar, and then it will be hard to say, is it just because they are different, or is that because they are model generated badly, poorly? But yeah, I think with adversarial network, or the thing I was also talking about, like the self-supervised with the SimCLR or algorithm like that, you can try to see if your network compress the galaxy in very different position. It could mean that they are indeed different, and you have lost information in your generation. I think there's something to explore here.
Okay, thank you. Since there have been many questions, I'll just ask kind of one about your overall strategy, which is, you know, in deep learning, machine learning, AI techniques, of course, there are these corporate giants that are constantly revising the state-of-the-art techniques, and I know that you're aware of the literature of you know, new methodologies that people are inventing all of the time to try to crack a little, you know, a little bit that state-of-the-art statistics that people are trying to always demonstrate. And I was wondering, you know, in science, where, you know, of course, you're doing statistical comparisons with data, and you're trying to show that the methodologies that you're using actually produce scientifically reliable results. How do you leverage new technologies that are constantly changing without kind of going down rabbit holes and chasing you know, new techniques that may be short-lived? And I say this in the context of new techniques like stable diffusion, which seem to produce amazing, you know, we haven't explored that so much in astronomy, but amazingly realistic images. Yeah, so anyway, what are your thoughts on that?
Oh, yeah. So I mean, I think we are all concerned by this thing. Like you're proud of your model, and you see that in the industry everyone is in another type of model. But I think, for example, for transformers, so we thought about maybe we should go to use transformers, which could be interesting. But in the same time, when you look at the challenges and things like that, you see usually they compare and say, okay, we are better because we are 0.1% better in this specific metric. So I think it's good to explore different methods, but I think you shouldn't go lose a month to discover and be an expert in a new technique if you don't know before that it's really game changing. I mean, I think there's, I mean, diffusion and the transformers, things like that. think there were not game changing. It was a bit better in certain conditions. And I mean, I and in my group, we didn't took the break of transformers. And now we're saying, well, maybe it was a good choice because transformers are now overdated by diffusion methods. So I think it's a good hint that maybe NCNNs are still good if you don't look at the percentage change. So I think for now, I would try to better understand, better quantifying the uncertainty and things like that in models that we know than trying to completely change. Yeah, it's a bit of a faith leap. Say, okay, maybe this will be game changing, but you will lose a lot of time maybe for nothing. Some of us could do it, but yeah, I think I prefer to stay on something I know and try to better understand, because I mean, even CNNs, we don't understand what they're doing. So there's still a lot of work to do on that.
All right, excellent. Thank you.
Thank you, Ray.
Thank you very much. So before moving to your supervisors, I think I'll ask my questions. I think it will be better like that, so that you're finished with the most maybe stressful part. So and unfortunately, there were many questions asked. So I think that my questions will be somehow a reformulation of some of the questions. And I'd like to just before starting, congratulate you with all your work, because it was really impressive to read all what you've been doing. So I had the pleasure to see you here at IAS. As you mentioned, you made your PhD in 3 labs, 2 countries, with 3 people. So that's already kind of an achievement. And I liked very much the way that you have explained all the context, all the background science and background description for all the methods, etc. And then I wanted to have your opinion on several very overall naive questions on the emulation. So you've been using the VAE and FVAE for the emulation. And my question to you is, do you think that this is basically the ultimate thing that we can do? As you mentioned, now, of course, there are new things that are coming out nowadays. So is this really the optimal solution that we have? Or in other words, what are the intrinsic limitations of these approaches? Yeah. And you mentioned it a little bit. There are other generative models, and the GANs are some. So of course, the GANs have their limitations because you need to have huge data sets for trainings, etc. But imagine that you had the as large data set as you want for the GANs. What would be basically the difference between the outcomes in terms of the emulation from one or the other?
So to answer first, I don't think, to be honest, I don't think that at least for now, the deep learning generative model is the perfect thing for a galaxy emulation or simulation. But if you want to do a precise science to really understand how galaxy evolve and things like that, because as I said, you don't have a perfect way to know how realistic you are. So maybe you're gonna have biases that come from the model, but also that comes from your data, and it could be problematic to base your galaxy evolution science on that. It's one of the tools, and for example, in our case, I mean, we didn't study galaxy evolution. We use this to challenge the softwares and things like that, where I mean, if there is small problems that can be non-real for galaxy evolution, is not a big problem because you want to challenge your softwares. To base all your science on the techniques that are for now deep learning, I won't recommend it, even if I do deep learning and things like that. Maybe in the future we would, and we could. For now, I think we need to keep the TNG simulations and things like that. Even if, for example, another way to compare if the simulation are good is to compare, and I know people are doing that in the ESA, for example, to compare TNG simulation with deep learning generation, but
So one additional or maybe continuing question is the fact that as you mentioned it yourself, the fact that you basically condition on parameters, and those parameters that you are conditioning on are parameters which are profile parameters, which is basically 1D symmetrized information. And then those objects that you're trying to emulate are 3D. They depend on the redshift, and there are implicit parameters, like for example the environment. So you mentioned that we can condition on a more complex set of parameters. So what's the limit? How far should we go to make it as realistic as possible if we were to follow the path that you have been starting?
So I guess one of the possibilities is to get rid of this flow, which is based off a limitation, because then you need a catalog. And you could just train a very accurate VAE and then just randomly produce galaxies that have more chances to be very realistic. But you will lose the condition on the parameters. But maybe if you just want to produce a big data set of complex morphologies, this is a way to go, because the flow is just a limitation. The other way, if you could condition your flow with all the columns of your Euclid galaxy thing, would be great. But the problem is that you will never have enough data set large enough to have. This is a curse of dimensionality. If you add dimensions, your density of points inside this space decrease exponentially. So the more you condition, the less objects you have that have exactly this conditioning, and so you train worse.
So for example, if you use a covariance matrix of all the parameters and then search for, I don't know, their principal components, or I don't know, their eigenvalues, etc., would this be something that could be viable, or not at all?
I'm not sure to understand the idea.
Basically, finding out what are the most important, the most important,
the most important parameters to condition on to create realistic. But here again, I think if you just want to create realistic morphology, you don't condition on any parameter.
Okay, that will be maybe my last question. It's about the detection and segmentation. So maybe I didn't understand perfectly, but well, limited is not what I meant, but what's the limit related to the fact that you have an underlying model, which is your SERSIC model? So if you had I mean, how much is it dependent on your hypothesis?
Well, first, you're never sure in deep learning that your model will be able to adapt to more complex things, knowing that you will always have seen blobby things. Will you be able to see a bit more complex things? The second thing is that you can't train it on complex morphology, such as what's the difference, which is really hard to say even by eye, between a clump of stars in a galaxy, in a spiral arm, and a spiral arm galaxy without a clump, but with a galaxy on the forehand or background. And this, if you just use SERSIC profiles, you won't be able to test. Which is, again, for cosmology, it's not such a problem because this precise case doesn't appear that much. For local universe and morphology galaxy, it is a limitation. But I think if we test our algorithm on real data, it will over-deblend. That everything that there is a bit of a structure in a galaxy will say it's another galaxy. I didn't make the test, but would make sense.
Okay, so thank you very much. I think that I'll finish here and just congratulate you for these fantastic results that you've been showing for your PhD, and thanks a lot for the answer to the questions. And now I'll take my hat of chairperson of the committee, and I'll switch now to your supervisors, and I'll start with the first whom I see, Alex from APC Paris. Please go ahead with your questions.
So on page So I won't ask questions, of course. We have had too many. But if I'm alone, I will switch to French.
Please go ahead.
Ok. Je tiens à te féliciter pour cette thèse, une très très belle thèse. Je pense que tout le monde l'a reconnue. Moi, c'est la première fois que j'avais le plaisir d'encadrer, de co-encadrer quelqu'un. Et en fait, c'était facile. Avec toi, c'était très facile. Donc ça, c'est quelque chose qui, pour une première thèse, c'est toujours très agréable. Et donc, j'ai eu le plaisir de te découvrir et de voir quelqu'un qui était toujours joyeux, toujours avec la joie d'entreprendre, d'essayer de nouvelles choses. Donc, c'était un moment extrêmement agréable. Ça n'a pas été facile, je tiens à le noter, parce que quand même travailler dans plusieurs instituts différents à distance, il y avait le Covid qui a été important. Bon, tu étais à distance, donc ça ne changeait pas grand-chose, mais en tout cas, on a toujours maintenu un contact et une interaction. Donc ça, et ça s'est fait très naturellement, et j'ai toujours trouvé ça agréable. Progresser ensemble, et puis en fait, grâce à toi, j'ai appris aussi plein de choses, hein, parce que c'est vrai que c'est aussi comme ça qu'on voit la recherche, on évolue, et ce sont les étudiants qui nous apprennent pas mal de choses. Donc merci à toi pour ça. Je pense que Brent sera très content de t'avoir dans son groupe. Oui, bon, on arrive à la fin, donc je pense que je peux dire ça maintenant. Je te remercie, je te félicite pour cette belle thèse et pour aussi cette belle surprise.
So Marc Huertas Company from Observatoire de Paris, please.
Yes. So, it's easier to get with him. So, je suis un peu ému parce que je me souviens quand tu es venu taper sur ma porte il y a peut-être 4 ans, un jeune étudiant de M1, 5 ans, super timide. Et 5 ans après, tu es devenu un vrai collègue. Complet. Et quand on a proposé cette thèse, c'était une thèse extrêmement difficile et challenging. En fait, il faut mettre ça en contexte. C'est une thèse dans une collaboration avec 1000 personnes, à peu près 1000 chercheurs,
600.
sur une mission qui n'a pas de données et qui, tu savais, n'aurait pas de données pendant ta thèse. Et même comme ça, tu as pris le challenge sans hésiter. Et en plus de tout ça, c'est une thèse, comme l'a dit Nabila, sur 2 pays, 3 instituts, 3 encadrants, en plus des 1500 chercheurs utiles. Et ça a été vraiment, je pense, tout le monde est d'accord, un vrai succès. Tu as pris ça avec enthousiasme et je pense que tu as en plus le encore plus gros challenge de publier 2 key papers dans Euclid. Et ça veut dire 2 key papers dans Euclid, ça veut dire 1500 référis, plus 2 référis internes, plus le Euclid Internal Publication Board. Et je pense, je me trompe peut-être, mais je dois être le seul maintenant qui a publié 2 key papers premier auteur. Donc, bravo pour ça. Et tu as réussi vraiment à avoir un nom dans le consortium. Je pense qu'il y a peu de personnes maintenant dans le consortium qui ne connaissent pas ton nom. Et donc ça, je pense que ça va être très utile pour la suite. Bon, voilà, donc c'est vraiment, j'aimerais aussi que toutes les thèses se passent comme ça. Diriger, encadrer un étudiant comme ça, comme toi, c'est extrêmement facile, toujours enthousiaste, toujours envie de faire un truc, on propose un truc, oui, je vais le faire. Et en général, t'arrives au bout. Donc bravo. And I'll switch to English towards the end because you're going to Santa Cruz. So you're going to one of my favorite places in the world to work with an estimated colleague. So I think you will have even more fun. And I'm really jealous about Bran. Also Bran, because he will have the chance of the luck to work with you for a few more years. So have fun, and I hope to continue working with you.
Hervé, last supervisor locally here from IAS, Université Paris-Saclay.
So congratulations for your huge work. After more than 2 hours and 15 minutes on the spot, I guess you deserve a nice congratulations, well-deserved congratulations.
for your work for all your years. I guess you were so efficient and energetic that you needed at least 3 supervisors. So this gives the scale of your involvement. Maybe I can say a few words, just 4 quick points. About your insertion in the labs. You worked, it was mentioned, in 3 labs in different contexts, and each time that was very easy for you to be inserted in the lab very quickly. Your social skills were able to make you completely embedded very quickly in the whole community, so young and old. It was very a nice pleasure to have you. You took responsibilities in every lab you went into. You're not in your corner hiding and working, and well, you were working, but not hiding alone. And you were very. That's important in science too, to interact, as you know. And for the MER part of the science grant segment, I should also congratulate you and thank you for all your work you brought. You basically managed what many tried without success to basically connect everyone in MER and outside, and only for that, that's a big success. And your ability to work in large collaboration with different interaction is a key, and you did it very well. And so thanks and congratulations for that. Another point is you mentioned your willingness to share expertise in the context of open science. This is very important now in science. So I'm also congratulating you for that. It's the future, apparently. So and you did it completely. I mean, on your own. You had no input for that. You decided to do that. So that's very very important. It was mentioned. You as all of us, but lived the COVID and lockdown period. So from what you showed and what you wrote and what you published, it seems like you were on another planet without any lockdown or COVID. You managed it so well that has no, it does not appear in your work. So congratulations for that. I know it was not easy. I'm not saying it's not easy every day, but you managed very well. So it's also good quality for science. And finally, as we have seen, you had a very nice also ability to be very clear on the public. So you were very pedagogical, as we say in French. So it's a very good skill. And you mentioned, and I also saw you on different outreach events that you did very well, and I'm glad you enjoy it, because as you mentioned, it's very important also that science goes outside the labs and the university. So congratulations for that also. So it was a pleasure to have you. We will miss you. We are jealous on the place where you're going.
Yes,
mentioned,
yes.
but I should emphasize that too. And so, bon vent pour la suite.
So now, in the audience, people who have a PhD are allowed to ask a question to Hubert, if they dare. If they want. So, is there any person wishing to ask a question? No. So in that case, the committee members will go isolate to discuss densely about whether or not we will award you the PhD degree. So demandé si on allait t'accorder le diplôme de docteur. On a beaucoup hésité, hein, comme tu peux l'imaginer, parce que on s'est dit que finalement tu n'avais pas assez fait de choses pendant ces 3 ans, que tu n'avais que fourni à la communauté et à la collaboration liquide des outils qui sont, on va voir, et qui ont déjà un impact très très important dans la définition des capacités scientifiques de liquide. Avec le travail que tu as fait, tu as vraiment fait changer un peu la façon dont tu travailles dans une collaboration. Tu fournis des données qui sont réalistes et on en a absolument besoin pour la cosmologie de précision, la fameuse cosmologie de précision, n'est-ce pas, avec des paramètres au-delà des paramètres standards du CMD. Tu as en plus pris à bras le corps et avec une maturité remarquable un travail très compliqué, très ardu, très complexe humainement, de gérer un groupe de 20 personnes, 20 chercheurs en plus, hein, pas n'importe quelle personne, des chercheurs, tous convaincus de leur capacité à faire au mieux. Tu as géré ces 20 personnes dans un travail de comparaison en fournissant en même temps l'infrastructure pour faire ces comparaisons, en participant à ce travail, en orientant, en décidant, en discutant, en rédigeant un papier de la collaboration liquide. Tu n'as pas fait que ça, tu l'as fait avec énormément de maturité, une maturité qui se traduit par le fait que tu as été capable justement de gérer cette équipe, et une maturité qui a été capable, qui est en fait démontrée par ta capacité aussi à critiquer, à apporter un regard critique sur les résultats qui sont obtenus. La maturité, c'est quelque chose qu'on a souligné aussi, notamment dans le cadre de la réponse à des questions, très très nombreuses questions de spécialistes qui ont été posées, qui démontrent une profondeur de ta compréhension, non seulement des techniques que tu utilises et que tu c'est la perfection que tu masters, ça maîtrise en français. Je pensais que ça allait être plus facile en français, mais en fait non. Mais aussi une profondeur de compréhension des problématiques de la cosmologie de précision qui a absolument besoin de ces nouvelles méthodes de data science. Et donc, tu accompagnes les développements de la science en cosmologie, en physique des galaxies, avec des développements technologiques, de nouvelles technologies, mais aussi avec le recul, et ça c'est hyper important, et c'est vraiment une grande preuve de maturité. Tu as fait ça en autonomie et en indépendance, dans une période qui a été très compliquée pour tout le monde. Ça a été très compliqué pour les doctorants de passer cette période de pandémie, pour les postdoctorants, pour les jeunes chercheurs, pour les anciens chercheurs aussi, et pour les jeunes chercheurs, d'être dans l'incapacité d'interagir aussi facilement que tu pouvais l'avoir. Tu as réussi à t'en tirer plus que à t'en tirer. Tu as réussi vraiment à passer plus que ça. Alors, bien entendu, tu l'as fait avec le support de tes superviseurs, de tes encadrants, mais tu es l'élément moteur dans ce travail qui a été fait. Donc, ton indépendance et ton autonomie sont à mettre en regard de ton avenir. Tu vas partir en postdoc, tu es absolument armé pour aller en postdoc faire tes propres recherches, ce que tu as déjà commencé avec l'encadrement particulier d'encore plus jeunes chercheurs, des étudiants en master, dans des projets qui te sont des projets indépendants, et ça, on t'encourage vraiment à le faire. Donc voilà, on n'a que des jolies choses à te dire. On te souhaite tout le meilleur de la science. Alors, nous, individuellement, te félicitons. Malheureusement, il n'y a pas de félicitations du jury dans les thèses de l'Université Paris-Saclay, mais nous te félicitons tous individuellement pour la quantité de travail, pour la dévotion pour la communauté, pour l'impact de ta science, pour ton enthousiasme aussi, et pour ce que tu as apporté dans les différentes équipes dans lesquelles tu as travaillé, aussi bien ici que à l'ABC, à l'IAC, où tu as apporté ton expertise au service de tes collègues doctorants, postdoctorants et des chercheurs. Et donc, félicitations et bon vent, profite un peu de la mer là-bas et du soleil, et on t'en veut parce qu'on est jaloux, mais nous sommes très contents pour toi. Bravo à toi, Hubert. Ah oui, pardon, la phrase magique. Le jury ici présent t'accorde le diplôme de docteur en physique, spécialité astrophysique, de l'université Paris-Saclay.
Merci à tous. Je suis pas pleuré, je suis un peu ému. So first, I want to thank a lot all the jury for the long but very interesting discussion and question on the defense, but also on the manuscript. I think still have some work to do on the manuscript, and I think it will go very in a good direction with a really nice remarks. So thanks a lot. Then I think I'll go in French. Merci beaucoup à mes encadrants. J'ai des remerciements dans ma thèse, mais je vais aussi les dire à l'oral. Merci Marc d'avoir proposé ce sujet. Comme tu dis, ça commence à faire un moment qu'on se connaît et qu'on a quand même, je pense, en tout cas moi, bien évolué et qui est pas étranger. Merci pour tout l'accompagnement scientifique. Je pense. Mais jamais mettre la pression, mais toujours être là quand on en a besoin, mais laisser une certaine liberté. Alors moi, c'est vraiment l'encadrement qu'il me fallait, donc je suis vraiment super content de t'avoir. Puis merci pour les Canaries, c'est quand même cool. Merci Alex, aussi pour la même chose, son encadrement scientifique, la partie plus ML, code, etc. Mais aussi tout ce qui était à côté, et tu le sais, et voilà, je ne dirai pas, mais tu le sais. On se reverra à San Francisco. Hervé aussi, merci d'avoir rendu le projet possible. Merci pour ton encadrement, toutes les possibilités que tu m'as données, notamment d'outreach, comme on en parlait. C'est vraiment une partie que j'aime beaucoup et j'étais content de t'avoir, notamment pour ça. Beaucoup de remerciements. Parce que comme vous l'avez dit, donc cette thèse dans différentes équipes, c'est difficile, mais c'est super. Donc de tous les instituts que j'ai fait, d'abord l'IAC. En tout cas, il y en a qui m'écoutent on Zoom. I'll switch in English again. So thanks a lot for the 2 years that I finally spent in Tenerife. The Traces group was a really great place to start my PhD. And all people, and especially mini Traces, all people that make me feel that I was not the only one to feel stupid. Et voilà. Pareil à la PC, je vais dire tous les collègues de bureau, les 2 collègues de bureau. Voilà. Et super, même si c'était un petit comité un peu en dents de scie, présence, ça c'est des bons moments. Et puis, l'IAS, si tous les groupes de sciences pouvaient être comme le groupe Cosmo, les groupes biopiques, je pense que à la fois la recherche et les chercheurs se porteraient bien et mieux. Donc, merci de m'avoir accueilli dans ce groupe et de m'avoir apporté ce que vous m'avez apporté. Et pareil pour les étudiants, les postdocs et tous les gens de l'IAS. Même si c'est un peu loin, c'est quand même un super labo. Et merci mes potes d'être venus, tous de Limoges, quand même très loin aussi. Ça me touche vraiment que vous soyez venus. J'espère que j'oublie personne. Évidemment, ma famille, merci pour tout. Je dirai en privé, mais vous savez, c'est ce que je vous dois. Et merci d'être venu aujourd'hui. Et c'est bon, je n'oublie personne. Non, mais c'est... Ouais. Et on va pouvoir passer au pot, si vous voulez. So thanks again for the jury. And we will have then a party in a bar in Paris, a small gathering of people in Paris. Cosmo out. It'll be close to d'Enfer Rochereau, around, I would say 8, but it's still a bit, around 8. Close to d'Enfer Rochereau, the Charles-Quint. So the bar is ours. Ok, merci encore à tous et
Bravo.